Statistics 3, hypothesis testing, type 3, p-values. Okay, so we have two examples here in this slide. So we're going to start with the first one here, which is just basic, calculate the p-value for the sample statistic. Z is equal to minus 2.08. So what we're going to do is we're going to sketch our graph. And we see here minus 2.08 is roughly here. And even though we're testing minus 2.8, as I said before, at leave insert level, we're always doing the two sides, the two-tail test here. So we'd be looking at 2.08 on the right-hand side as well. Okay, and therefore our p-value in general is written as twice the probability that Z is greater than the absolute value of Z1, which is our minus 2.08 and our 2.8. But of course we can't get these values from our table, so we have to rearrange that formula. So basically what that means is that that can be written as the probability that it is 1 minus the probability that Z is less than the Z value. Okay, and we did a lot of these questions already. So in other words, that graph, you could look at it as there's 2.08 and everything less than that would be the 1 minus, then would give us this green bit. And then because this is symmetrical, I double my answer. Okay, so rather than remembering 2p times Z greater than the absolute value of Z1, you're better off learning your formula for your p-value, because it's not in your maths tables, as 2 times 1 minus the probability that Z is less than Z1 because of the symmetry. Is that okay? All right. So then if we look at the values in the question, our p-value is going to be 2 times 1 minus the probability that Z is less than 2.08. As I said, even though it's stating minus 2.08 in the question, we're looking at this symmetry on either side. And now all I have to do is go to my tables and I find 2.08. And if we look at our table, 2.0, and then we go across 2.0, and we go across to 0.8, you can see we end up with 0.9812. So if I multiply that out, I end up with a p-value of 0.0376. So we are not being asked to interpret it here in this first question. We're literally just practicing how to calculate our p-value. In our second example, we're going to look at what on earth does this p-value actually mean and what does it tell us. Okay, so if we're looking at the second one here, we're looking at medical consultants. So I'm going to go on to the next page. And we're told that the medical consultants for large companies are concerned about the effects of stress on company executives. We're given the mean systolic blood pressure of males aged between 35 to 45 years of age is, according to National Health Statistics, 128 and a standard deviation of 15. We have a sample of 72 males in this age group were selected, and their mean blood pressure was 130. And we're asked, first of all, to construct a 95% confidence interval for the mean and interpret the result. Okay, so it's really important that we interpret our result after we set up our 95% confidence interval. Okay, so how do we do our 95% confidence interval for a mean again? Yeah, well, it's our sample mean plus or minus our critical value, which is 1.96 because it is the 95% confidence interval, and that's times our standard error. So if we write down our values, our sample mean, we can see there is 130. Our standard deviation, we're told, is 15. And our sample size we're told is 72. So if I expand out that formula, we have our sample mean minus 1.96 times sigma over root n, less than or equal to our mean plus 1.96 sigma over root n. Okay, so if I put that in, we have 130 minus 1.96 times 15 over the square root of 72, less than or equal to the mean, 130 plus 1.96 times 15 over the square root of 72. So if I put all that into our calculators and simplify, we end up with 126.54 and 133.46. So this here is our 95% confidence interval for the mean. But of course, we're not finished there because we always have to interpret our value. Otherwise, it kind of defeats the purpose of statistics if we don't understand what it means. So what can we say? Well, basically this means that we can say, not with certainty, but we can say with 95% confidence that the mean, and again, I always try and put it in context. What are they talking about? Don't just say the mean. So the mean here in this case is the mean systolic blood pressure. And who was the mean systolic blood pressure for all male executives. And again, what age are they? Well, they're aged 35 to 44 in large companies. The mean systolic blood pressure for all males lies in the interval of 126.54, and we weren't given any units for that. Okay, so it's just 126.54 to 133.46. And what else can we say? Well, we can say that if we look, the national average lies within this value. And again, if we go back to the top there, we can see the national value was 128. In other words, the true mean lies within this range. Okay, so that is part 1. So part 2 then says carry out a hypothesis test using a significance level of 5% to see if there's evidence to suggest that the mean systolic blood pressure for executives is different to the national average. Now, if we were to just conclude based on our 95% confidence interval, we can see that we would say that the mean has not changed because our confidence interval is between 126 and 133, and 128 lies within this interval. So therefore we would say we fail to reject the null hypothesis. But of course it's saying here significance level of 5%, and because this example is with respect to our test statistic, we're going to go and do the test statistic for this. Okay, so part 2. We're going to do our test statistic, hypothesis test, using our 5% level of significance. So step 1 is always in our hypothesis test to state clearly our null and our alternative hypothesis. So our null hypothesis is that the mean has not changed. In other words, the mean is 128. Our alternative hypothesis is that the mean has changed. In other words, the mean is not going to be 128. Step 2 is our test statistic. So Z is equal to the sample mean minus the mean over the standard deviation divided by the square root of n, which can be found in our maths tables, our standard error of the mean. And if we sub in our values, then we have our sample mean is 130, our mean is 128, our standard deviation is 15, and our sample size is 72. So subbing our values in, we have 130 minus 128 over the square root of, over 15 over the square root of 72. And subbing that into our tables, we get 1.13. So as to be expected from our 95% confidence interval, we would be expecting it to be lying not in the critical region. But we're going to continue to draw our graph to prove that. So again, we draw a nice graph. Mark in our critical values of 1.96 plus and minus. Mark in our critical region. Then we label it our critical region. Anywhere in this region here, we fail to accept our null hypothesis. That's 2.5%. 2.5%, hence the 5% level of significance. And this region here, we would fail to reject. This is our 95%. Okay, so we now mark in our test statistic. So 1.13 clearly lies just to the right of 0. So that's 1.13 there. So that's our test statistic. And what we would say is 1.13 does not lie in the critical region. So it lies between so we'd say minus 1.96 is less than our test statistic, and therefore we make our conclusion. Well, what are we going to say? We would say 1.13 does not lie in the critical region. Hence, we fail to reject HO. And what do we conclude? Well, we conclude at the 5% level of significance. Always important that you're using that statement, okay? So at the 5% level of significance, that there is evidence to suggest that the mean systolic blood pressure for males aged 35 to 44 in large companies is the same as the national average. Of 128. Okay? So now if we go back to the question, There's one last bit of this where it says now we have to give a p-value for this hypothesis test and again interpret your value. So our p-value is going to be found by getting 2 times probability that Z is greater than the absolute value of Z1. And as I said, that is now going to boil down to 1 minus the probability that Z is less than our test statistic. Okay? And it'll always be the absolute value. So if we sketch the graph, well, what's our test statistic? Well, it's 1.13. And minus 1.13. And we'll be looking in that region there. So therefore, again, looking at our two-tailed test here, our p-value is 2 times 1 minus the probability that Z is less than 1.13. So as I said, we're always taking the positive value when subbing into this formula here. That's why we're doubling, because of the symmetry. And then what we do is we go to our tables to find out what that value is. So if we go to our tables, where's 1.13? And there's 1.1, and we go over to 1.13. So 0.8708. So if we put that into our calculators, what does that give us for our p-value? Well, it gives us 0.2584. So this is the first time now we have to interpret what this p-value actually means. So remember, if p is low, HO must go. So when doing our p-value, we should always state our significance level. So our significance level, alpha, is equal to 0.05. So that's our significance level. Okay? And therefore, we're comparing our p-value to this significance level. So we can clearly see that our p-value, if we compare it to 0.05, is much greater than 0.05. And therefore, what do we say? Well, we say that there is insufficient evidence against the null hypothesis and hence, so we say therefore we fail to reject HO. So this is basically giving us further evidence that we are failing to reject. So we saw we'd failed to reject from our 95% confidence interval because 128 lies within the region here. So it's between these two values. When we looked at the test statistic, we saw that it lies outside of the critical region, so it's not in the critical region at all. It's in the fail to reject zone. And then our p-value has now confirmed it even further by showing that the p-value is much greater than 0.05. So essentially your p stands for probability. And you know, if you want to test some claim and to make sure that there is an actual change, what you want is your p-value to be low, in other words, less than your 0.05. And therefore what that means is that the probability that it has happened by chance is very low, and therefore there is definitely evidence in your claim that there has been a change. Where if the probability is high, then you can't go against the null hypothesis. Okay? So what I'm going to get you to do now is go to page 159 in your book, and you're going to do question 4, question 5, 6, 7, 8 and 9. And when you're done those, you're finished the course. Yay!